Okay, today we start lesson 8, which is on hurricanes, still in module 1. Please note that hurricanes are called typhoons in the Northwest Pacific and cyclones in the Southwest Pacific and Indian Oceans. All of their energy sources latent heat. For us, the name hurricane is derived from Huracan, which is the Carib god of evil, so you know how they feel about that. They're usually 60 to 900 miles in diameter, so they can be either compact or really big. They form between 5 to 20 degrees latitude, and they have a steep pressure gradient. Now, they rarely form outside of these zones that you see here highlighted. There was one recently in the southern Atlantic Ocean, but generally speaking, the geographic features here don't really allow for hurricanes to form. But it's not impossible, so it has happened. And also over here, same reason. So actually there's more cold water here, so that's why. But out of many tropical disturbances, only a few will hit that hurricane status. So you don't really have to worry about every tropical storm coming to kill you. So why do we care about this? Because the coastal counties of the United States are home to over 128 million people, or almost 40% of the nation's total population. Yet the coast accounts for less than 10% of the landmass, which is interesting. So we have like a lot of people in small areas. And during holidays, weekends, and in the summer, the population can increase to almost 100-fold. And even though 80 to 90% of the population live in these storm-prone areas, most have never experienced the core of a hurricane. However, it's probably only a matter of time. So here we have, just highlighting Florida and the Gulf Coast, you see so many people. This darkest blue is over 500,000 people in those little counties. So we have a lot of people being in those storm-prone areas. So let's talk about hurricanes. A hurricane is an intense center of low pressure that forms over tropical or subtropical oceans. It is characterized by intense convective activity and strong cyclonic circulation. They look like so. And I have a storm track here for a hurricane, and it goes through a series of stages, which we'll go through later. And when it's a hurricane, it can last for several days. So that's why I put that there. So you can see that these are large storms. They last for multiple days, sometimes multiple weeks. So it's different in the tropics. The tropics are considered between the Tropic of Cancer, which is 23.5 degrees north, and Tropic of Capricorn, which is 23.5 degrees south. There's no temperature contrast when it comes to these storms. So when we built our mid-latitude cyclones last week, those were based on temperature contrast, right? We had a polar air mass, we had a tropical air mass, and they are interacting with each other. This is no air masses. So there's no air masses, there's no fronts, but it still has a steep pressure gradient. So we'll get to why that is. And by the way, these kind of images, you might see them in the news. They are a satellite image seen from space. It has been color enhanced so that we can see the features of the clouds as atmospheric scientists. So the cloud is not really red, okay? It's actually just colored that way so that we can tell these are really high clouds, which indicates stronger thunderstorms in that area. Okay, so hurricanes are basically giant heat engines. They're fueled by latent heat when it's liberated from the surface of the ocean. So we have this water vapor, it's being evaporated from the surface, and then it's condensing into clouds, and that release of latent heat warms the air, which then provides more buoyancy for upward lift, which reduces our surface pressure, which then leads to more inflow of air, and then the whole process repeats. So it'll just keep going until the environment no longer allows it to do so. So this picture kind of shows you, we're going to move in towards the low, it's going to move up, condenses into cloud, and then it continues to do so. So pros for our hurricane formation include, number one, warm sea surface temperatures. So sea surface temperature of at least 27 degrees C or 80 degrees Fahrenheit or higher is required and necessary to provide that heat and moisture for our storm. And this is a satellite image from the beginning of hurricane season. This is June 1st, 2010, and you can see it has been colorized for 27 degrees C or higher. So that's all the warm colors here. So the warm colors indicate that is minimum temperatures for our hurricanes to grow. So you can see even in June, it's already warm down there. So it's getting ready. Please note the Gulf Stream here. It's a little guy right there is one of our currents. We'll go through ocean currents in a later class. Number 2 for our pros is an easterly wave. So these generally move from east to west, hence the name, easterly wave. So we name things from where they come from. So on the east side of the axis, we have this convergence. Hold on, I gotta move my face. Okay, there we go. So you see the convergence on the eastern side and then divergence on the other side. And what happens is the clouds kind of get stuck up on one side. So you see down here, a couple of clouds. And so that adds to additional lift in this kind of disturbance, which we'll get to just now. So it's called a tropical disturbance. This is point number 3. So first, warm sea surface temperatures, then we need an easterly wave, and then we have this tropical disturbance. So this is a disorganized array of clouds and thunderstorms. I like to call them cloud blobs. They exhibit weak pressure gradients or none at all. It doesn't have any rotation yet. They form in the tropics, of course, and so it can interact with the ITCZ, which is a convergence zone that's around kind of it's like a belt going around the Earth. So that can add even more convergence lifting if it's near that. And any troughs from the mid-latitudes can also enhance development. Another pro is Coriolis. So yes, Coriolis affects our hurricanes as well, which is why they do not form within 5 degrees of the equator. So remember, there's no Coriolis at the equator, so there's not going to be a hurricane because the hurricane needs to rotate to get going. So we need a weak to moderate Coriolis in order for our storm to spin, which you can see here, right? So no Coriolis, it's all just going to move to the center. It doesn't spin. But with Coriolis, we see there's some spin up in a counterclockwise direction in the northern hemisphere, which is what we need for our hurricane. Okay, so they form mostly from late summer to early fall. That's kind of when we peak. And the season runs from June 1st to November 30th. Although it is being considered to change that. So we'll see if that happens based on some recent seasons. So here's total number of hurricanes in red. The other color, I guess, is orange. And it shows you number of tropical storms and hurricanes. So we see the total number of storms that happens every year is much larger compared to what actually becomes a hurricane. So keep that in mind. Like I said, peak is August to October. So we see there, we're just coming out of that now. It's October 7th when I'm recording this. So we're coming out of the peak season. Hopefully it'll quiet down because we're almost out of names, which we'll get to a little bit later. So a couple of cons now. So that's going to be against formation. We have a trade wind inversion. This is a strong inversion associated with the subtropical high, which diminishes the ability of the air to rise. So it inhibits our growth of thunderstorms. So you see on the right, this is a trade wind inversion. So instead of them moving up like they should be doing, it slowly kind of smushes it down. So this subtropical high inhibits our growth of thunderstorms, which obviously we need to make a hurricane. So that's bad. Bad for a hurricane. Okay. Number 2 is strong upper level winds. So this disperses our latent heat and removes it from our cloud tops. Also, any continued storm growth will be inhibited as well. So we see here weak shear is favorable because we want to spin up the storm. So a little bit is okay. But if I get too much, it's unfavorable. It'll just rip the storm apart. So you might hear on the news where they'll say the wind shear is too strong or chaotic for the storm to get organized. And that's absolutely legitimate. The storm will rip apart. So that's bad for our hurricanes. Now, in the past, when Flash used to work, thanks Adobe, not a sponsor, they had this game to make a hurricane. and you go through and set all these environmental parameters, and then it would create the hurricane digitally, right? It would make it's a game, okay? It was for little kids, but it doesn't work anymore. So sorry about that. We move on. Okay, so this is the stages that we go through to make our hurricane. All right, so we start with a tropical disturbance, which then has the latent heat being released. So the area within the disturbance warms, the air density lowers, surface pressure over here drops, right? So we have a weak low pressure now and a cyclonic circulation. Then, as my surface winds increase, it brings in more moisture into the storm, which adds to the growth of the storm. More water vapor condense, which leads to more latent heat, which is what our storm feeds off of. So the heated air rises, there's adiabatic cooling, more condensation, which increases the buoyancy, and then etc., etc. Like I said, this will continue until it no longer can. So here's our different stages. First of all, a little definition. Sustained winds is the winds averaged over a 1 minute interval because it's kind of chaotic inside the hurricane. So we're talking about an average over 1 minute. And the first stage after that disturbance is it goes to a tropical depression. This is if wind speeds are less than 39 miles per hour. So there's our disturbance or tropical wave. It looks like that from space. It's pretty disorganized, just looks like a bunch of showers. Then once we reach depression, it has a circulation. So you see it's sort of organized here. Then it will move to tropical storm status, which is when the winds are between 39 and 74 miles per hour. And it becomes, after it becomes a tropical storm, it's given a name. So if the tropical storm becomes a hurricane, the name stays the same. Here's what it looks like, right? A little bit more organized as well. And then as it moves into a hurricane, the winds exceed 74 miles per hour. Storm becomes category 1, which we'll talk about in a minute. And it looks like so. It might start developing an eye, and that's very characteristic of these storms. So the eye will get clearer and clearer, generally speaking, as it gets stronger. So each year we have between 80 and 100 tropical storms develop around the world, but only half of those roughly will reach hurricane status. So again, not every tropical storm is coming to kill you, okay? Relax. So what about, let me move my face again. How do I get rid of it, right? That's all we care about. How do I get rid of this storm? It sounds really dangerous. Okay, well, hurricane decay occurs after I cut off its food supply, which is the latent heat. So if I can move it off of the ocean, voila, that will happen, right? So moving on to land is the best possible scenario. It isn't for the people who live there, but to get rid of the storm it is. So we've cut off its food supply, plus we have an increase in surface roughness, which is called friction, okay? That will reduce its wind speeds. And when large-scale flow aloft is unfavorable, that trade wind inversion that we saw earlier, that will also diminish its intensity. And yeah, so here's it's not really a recent example, but a example of this kind of dynamic. We see Hurricane Fran from 96, I know. So here's Hurricane Fran moving towards the coastline, and we see the central pressure here is like 988 millibars, which is nothing to sneeze at. So after 1 day, 24 hours, we see Hurricane Fran has moved from a hurricane to a tropical storm. It now has 980 the center here is 954. What am I saying? Now it's 980. So it's moved up in millibars, which means it's lost its intensity a little bit, very slightly here. And when it moved inland, it caused heavy rains, flash flooding. It killed 30 people. Unfortunately, it caused more than $3 billion in damages. So what happened? When it hit the land, lost a lot of strength, and then eventually it will dissipate. So, profile of our hurricane. Something important when it comes to hurricane is something called conservation of angular momentum. You've probably seen this when you watch figure skaters, like during the Olympics. When they pull their arms in, they spin up faster, right? That's the same idea here in our hurricane. So as the air moves towards the center of the storm, it will actually move faster because of this conservation of angular momentum. So the velocity increases as we go into the storm. And we see that warm, moist surface air going into the core of the storm, which turns upward. So you see over here, coming into the storm, turns upward in a cyclonic fashion. It ascends in this ring of cumulonimbus towers, so really, really tall thunderstorms, and that makes the eye wall. So the eye wall is the donut shape, that's what the book calls it, the donut shaped wall of intense convective activity surrounding the center of the storm. It's like someone was really hungry when they made these definitions. Anyway, it has the greatest wind speeds here, this side and this side, and also the heaviest rainfall. So the rest of the rain is going to wrap around the storm. Kind of looks like octopus arms kind of going out from the center, which you'll see a little later on the radar image I have for you. So they trail away in a spiral fashion, it says. Now the top of the hurricane actually has a small amount of air that descends through the middle, and that warms by compression, which produces a cloudless sky, and that is called the eye. So that's what kind of makes it different than the mid-latitude cyclones, besides the fact that it doesn't have air masses, is it has this kind of center donut, which has a hole in it, right? The storm has a hole in it, and it's caused by that warming and compressing air. So hurricanes need that energy, that latent heat that we talked about, so it kind of limits the areas where they can develop. So this kind of highlights those areas for us, and I like that it's labeled like what they're called there. So these are hurricanes, and then some of these are called typhoons over there, but typhoons in the Western Pacific, and then cyclones over here. And where they come from, that's where the water temperature reaches that minimum threshold that we talked about before. All right, so during World War II, tropical storms were informally given women's names, perhaps after wives or girlfriends, because it was being monitored by the Army. And then from 1950 to 1952, tropical storms were given names by the phonetic alphabet, which was Abel, Baker, Charlie, etc. And then in 1953, the National Weather Service moved it back to women's names. And then until 1978, the list contained both male and female names. And now we've moved to a 6-year cycle, and it repeats unless the name is retired. So we see here, I have a list that's really old, but right this year I'm recording in 2021. So that would be the 2015 list, which is right under my face, of course. But we are now at Victor. So Victor just formed. So Victor is the second to last on the list. And what it used to do is it would go to the letters of the Greek alphabet, right? So alpha, beta, gamma, delta, epsilon, etc., etc. But recently, it was determined that these names are confusing to the public. So here's what's happening. It's from Scientific American, but you can find it in the news anywhere. They've determined that hurricane names from the Greek alphabet are being dropped. So they're going to stick with, quote, human names to lessen confusion and distraction. And this was published in March of this year, and it looks like it went into effect for this year's storms. So again, going back to class, if we exhaust this list of names, which we almost have done because we're on Victor, if we get to Wanda, and then there's another storm after that, it will now go to the supplemental list that they have set aside for, I guess, extreme seasons. So we'll see how that goes. Okay. Hurricane destruction. So the Saffir-Simpson scale was developed to rank the intensity of hurricanes based on their pressure, winds, and storm surge. Sometimes the intensity of storm will be called a major hurricane or a super typhoon. This is when it's category 3+. So you see here, wind speeds of 74 to 95 has, quote, some damage, and it's a category 1 storm. But then these 3 through 5 are highlighted in red, indicating that they are major hurricanes. Now I stole this one on the right. I'm going to move my face. From a USA Today book. It's called The Weather Book. I believe it's called The Weather Book for U.S. weather. and it's from like 1992 or something. It's so classic, but I love these little images, so I always use this. So category 1 through 5, and then it has a little simulated area near the coastline to show you the kind of damage we're talking about. So category 1 storm only has like one tuft of tree coming off. The house is relatively safe, and we only have a small storm surge of 4 to 5 feet, right? Then as you move to 3, I'm going to skip 2, go to 3, winds are between 111 and 130 miles per hour, and the storm surge is 9 to 12 feet. So now our house is damaged, we see the roof is damaged, window has been exploded, and the tree is starting to be blown down. If you move to 5, which is the highest category, we see winds are now over 155 miles per hour, our storm surge is more than 18 feet, and the damage is catastrophic. So you see the building is completely destroyed, and the tree is basically airborne. So I just love how extreme it shows the damage. It's not funny, but yeah. Anyway, it's a good way to see the damage. So how do we estimate this intensity? Because obviously someone's not out there with their wind meter being like, oh, what's the wind outside in the hurricane as they're like being blown away. No. So it says accurate observations are needed, but sometimes difficult to obtain. That is definitely the case. So winds aloft are stronger than those at the surface. In 1997, they developed this little thing called GPS. You might have heard of it, Global Positioning System. So we made these things called drop sondes, or drop wind sonde is the full name. And it is an instrument package that measures wind speed, direction, humidity, and pressure as it falls through the hurricane. So here you see, oh, there's my drop sonde. It has a little GPS, and then you go and pick it up. It radios back the data first, but then you go pick it up. No littering, right? Also, we use satellites. So satellites make it easier to detect the development of hurricanes, monitor its movements. They are remote sensors, so it's not super accurate, but I can tell, like, oh, it's more intense on this side of the storm, right? So that's better than nothing. You can also take kind of cross sections through the storm. So this shows you the pattern of rainfall in a hurricane, and they found these things called hot towers. This is from recent research. And they found that these massive cumulonimbus towers that exceed 7 miles high, that's one storm 7 miles high, that's pretty crazy, develop in the eye wall 6 hours before the hurricane will intensify. So that's helpful to know. So if I see those, I know the storm is going to intensify. This shows where a couple of memorable hurricanes where they tracked. The solid portion is where it was hurricane strength, and then other would be not hurricane strength, tropical storm, depression, what have you. So the most famous one is the Galveston storm. This is the first one on record in the United States. Completely leveled Galveston. So you'll see that in a second. We'll talk about that. Here's Camille in 1969. That one kind of affected our area here. Andrew slammed into Florida really, really bad. Katrina, of course, which went over Florida and then went into Louisiana. I remember personally Hurricane Floyd because we got out of school and there was like lots of flooding. So all of our drainage ditches in the eastern shore were filled with water. So like there's about knee-deep water. My sister and I went out and kind of walked around in it. Anyway, so hurricane tracks. Oh, wait. You'll notice that they all kind of move in the same direction, right? They move towards the west because they have easterly flow here. So there's easterly flow here pushing it this way. And then once it makes landfall, it gets caught up by the westerlies and pushed back out to sea. Thank goodness. Otherwise, it just sit here and like destroy everything. All right, so here's Galveston as promised. And in class, we take a little Google Map adventure. I guess I could do that. Let's see. Yeah, so here's Galveston. And if you didn't know, you can zoom in. Let me use the plus button. So here's Galveston. It's on an island. And what you can do, I'm not doing so well with this. You can take the little man down here in the corner. You can drag him and drop him on the blue highlighted areas. Super fun. And then you can see what it looks like right there. So this is super awesome. I love this. So there's the Galveston Pier. I don't know if that's famous or not, but there it is. And anyway, the point of showing you this is not to show you cars and pavement, but to show you just how close they are to the ocean and that there's literally nothing that would stop a hurricane from destroying everything. So you would just, like, the storm surge would just come over this and like the highway would disappear, everything would be underwater. So in that case, that storm was just like so bad. And then also we see, go back, that entire blocks were swept clean because we made everything with sticks and bricks, right? So sticks, bricks. The brick buildings did a little bit better, which is, I guess, a good thing. So a couple of churches still standing here, brick buildings. That might be a bank. I'm not sure what that is. And then we see just everything else was completely destroyed. Mountains of debris. Here's people for scale. It's like, how do you even begin to clean up? It's just, it's crazy. And they had no warning because they didn't have satellites back then, right? So it just kind of got darker and darker, and then you're like, what's happening? And then suddenly it's like, whoosh, right? So a super great disaster. Now, something we have now is aircraft reconnaissance. So we have a special plane that was built to go in and through hurricanes to provide snapshot data. And it is limited by its gas tank, obviously. So it can only be about 250 to 300 miles from the shore, and from, shore where the airport is and the plane is to where the hurricane is. So they have to wait for it to get close to go out, and then they throw the dropsondes, chuck them into the storm, and that's how we get some data. So they also have instruments on board, I'm sure. So here's the radar. Again, also limited to when it gets closer to the coastline. So it's 320 kilometers from the coast. It's monitored by this Doppler weather radar. So I can tell not only the precipitation amount, I can measure how much is going to fall, and I can measure wind speed and direction because of the Doppler effect, basically, which is a little bit of science. So here's the rain bands we talked about. So you can see that just kind of like spiral out like octopus, right? Center of the storm is right here. We can tell is the most intense center there, although this one's giving it a run for its money. But yeah, the center of the storm is right here. That's Tampa, by the way, Sarasota, Everglades City, Daytona Beach is over here, just to kind of show you like the storm is basically blanketing all of Florida. So it's pretty big, this one. All right, also data buoys. They are launched and they float out in the ocean. They're remote sensors as well, and they are fixed in different locations along the Atlantic coast and the Gulf Coast. They're anchored to the bottom. They sit there, they measure wave height, surface temperature, etc., etc. And right now it beams back to the computers and we have that data. So that's also helpful. Then we launch these things called Hurricane Watch. That's 48 hours in advance. You're like, whoa, professor. Okay, so tornadoes are only like 3 hours in advance. How come this one's so long? And it's because hurricanes move so slow. They're so big, it takes them a long time to get places. And we want to make sure people are having time to evacuate before it gets there. So hence 48 hours in advance. It's 2 days in case you are keeping track. So here we see the hurricane warning is where we think the hurricane is most likely to hit. Hurricane watch is on the outside of that in case we get it slightly wrong. And then behind that is going to be tropical storm watches and warnings. So notice how far inland it goes. So let me go to the warning. The warning is 36 hours in advance, and that's from tropical storm force winds. So that's 39 plus, right? And so we're not even talking about hurricane strength. We're talking just tropical storm force winds. And these will remain in effect when there's dangerously high water and waves to continue. And so we see in this case, it was aiming for Orlando, apparently. That was Dorian, yeah. So this one is Hurricane Dean from 2007. Just to show you what the track forecast looks like. I think it's unfortunate and needs to be changed. But anyway, you have a current location, and then an estimated position, and then this cone of uncertainty. That's what they call it. Big area. So basically what this means is if the hurricane ends up being over there, over here, it's still in the cone of uncertainty, so I'm still right. We got to work on this, guys. This is not, I mean, that's anywhere from basically Costa Rica to the Bahamas. It's like this big swath. I have no idea where it's going. Either tell them that or, anyway, I'm getting off my soapbox. We're moving on. So, hurricane destruction. Hurricanes are known for the 3 W's: wind, water, and waves. So, wind damage, again, just like tornadoes, they can turn objects into missiles. We have high winds spawning tornadoes. This was recently found. This study in 2004, published in 2005 in the Bulletin of Meteorological Society, American Meteorological Society, or BAMS for short, that's what we call it. They found that from the 2004 season, all of these storms spawned tornadoes with the hurricanes or Tropical Storm Bunny. And these are like large amounts, right? 117 tornadoes from Hurricane Francis. So it wasn't really well understood that hurricanes could spawn tornadoes, I guess, before that time. So now it's kind of been like confirmed. So we now know for a fact that hurricanes can spawn tornadoes. They can also produce lightning. So surprise! It's like, what? But they have a good deal of lightning with them. Mobile homes are particularly vulnerable. Do not be in a mobile home. Definitely, if you're in a mobile home, you should evacuate if there's a hurricane coming. Like, that's just a no-brainer. So we're going to pretend this is miles per hour for the sake of whatever. And what I'm trying to show you here is that this right quadrant, top right quadrant, is the most dangerous in the northern hemisphere. So why is that? It's like a right hook. Except for your boxing, it's like a right hook because we have the movement of the hurricane, which we'll say in this case is like 20 miles per hour, and the wind on that side is moving 175 miles per hour. It's a little bit of vector math. You add them together, you get a total of 195 miles per hour. So, sorry, I changed the numbers for you, but basically it adds the speed of the hurricane to the speed of the wind. That's why it's most dangerous. Now, on the other end, that bottom left quadrant, not as bad, but still 125 mile per hour winds, it's still nothing to get, nothing to sneeze at. It's still bad. It's just a little less bad. That's my point. All right, the second W is water. So obviously we would expect heavy rains, inland flooding, torrential rains, which cause these flash floods. So I think this one's from Maria. I was trying to think that. I believe it's from Hurricane Maria, which was Category 5. And we get flash floods, mud flows. Some can occur weeks after the storm has passed because we've now saturated the soil, so that's bad. Lots of debris, lots of waves and wind. So those waves come from the storm surge. So the storm surge is a dome of water, 40 to 50 miles across. It occurs where the eye makes landfall. So the water is piled up from the surface winds, plus it comes from like a suction effect. This is a little gross, but go with me. It's basically like if you take a toilet plunger, right, and when you plunge, you're pulling the water out, right? So it's the same thing with the low pressure. It's pulling the water up, plus we have surface winds piling up the water. So you get this big dome of water moving on shore. Shore's down here. Here's the water, and it just goes over top of it. So that's what's happening with the storm surge. Sorry for my bad hand motion graphics, but so here's a picture. You see the mean sea level, normal high tide, unsuspecting house, right? I'm sorry, spoilers, the house gets destroyed. So when I say storm surge, I mean water on top of normal high tide going onshore. So here we see that happening, and oh dear, like I said, house is destroyed. So here's number of deaths associated with hurricanes to strike the U.S. mainland until 2011. Okay, so this has not been updated. This is from like a previous textbook. I will eventually update this. The most famous, most devastating to hit the United States was Category 4, the Galveston hurricane in 1900. You're like, okay, well, how did they get that information? These are estimated from journals, newspaper articles, etc. So it's been estimated 8,000 people, but it could be as high as 12,000. It's a lot of people. Again, no warning. So they didn't have a chance. And then a lot of the other storms here, 28, 35, 26, 09, all of these are kind of early 1900s. And that's what we'd expect. Higher death rates when we don't have a warning system, we don't have satellites, we don't have meteorologists, basically. Meteorology didn't really become a big thing until after World War II, so that kind of makes sense. Now, the one that upsets me the most is Hurricane Katrina. Hurricane Katrina, now ranked at number 3. It was actually Category 3 at landfall. That has been revised. This is 2005, in case you don't remember. The death rate is now somewhere in the 2,500s, I believe is what the recent thing I read. And to me, that's just unacceptable because, like I just told you, all this technology that we had, they were told to evacuate, and then it was just a disaster that didn't need to happen. And that's all I'm going to say about that. Okay, so complicating factors, you could have a pre-saturated ground. What if it's already rained a lot? If that happens, we'll have even more flooding, right? Or what if it arrives during high tide, right? The moon causes high tides, plus the position of the sun. You could have a king's tide plus the storm surge. That's going to be even more bad, right? And then that northeast quadrant, like I said before, has the maximum impact in the northern hemisphere. Okay, so this is kind of funny, but stay with me. So we did do cloud seeding when it comes to hurricanes. Yes, we did. We called it Storm Fury. It was a joint effort by the National Weather Service and the U.S. Navy. It was supposed to diffuse the strong winds from the center of the hurricane. That was the idea. So they put the silver iodine released in different locations within the hurricane circulation, which would then force condensation and force the heat release in other zones besides the eye wall. Again, I'm trying to get rid of the eye wall, right? So the hope is to deliver a less defined single center of concentrated heat release and lower pressure, so the pressure field will be less, the wind field will be more confused. So did it work? Sort of. So in 1963, there was Beulah, again with the names, right? They're not really scary names. And Debbie in 1969, they were a success, but it was argued that what if it had dissipated on its own and had nothing to do with our seeding experiment? So we don't really know. The answer is unknown. So unconfirmed results, and then it was abandoned in 1990 because, But I've heard all kinds of theories like, oh, let's drop a nuclear bomb into the hurricane and get rid of it. Or let's put giant fans on the Florida coastline to make the hurricane blow away. Those are not good ideas. I'll just put it that way. So then in class we watched these two. This is Andrew making landfall. Pretty scary stuff. And then this one's Hurricane Laura from last year, 2020. And I think that one's scarier, honestly. But this lady's standing out there in the storm, of course. So here's your vocabulary. And we just played these games about preparing for emergencies. So it goes through how you should prepare for a hurricane, how you should prepare for a thunderstorm and tornado. So that is the end of class. And I will see you next lesson. Bye.